Hello everyone, welcome to the video lecture series on Chemical Engineering Thermodynamics 1. Myself, Jaimin Pandya, Assistant Professor in Chemical Engineering Department of LJIET Institute of Engineering and Technology. So let's continue with the chapter Thermodynamic Properties of Fluids. So in this lecture, we'll derive various mathematical relations among thermodynamic properties. So in this lecture, we'll derive various thermodynamic properties such as deriving equation for the entropy calculation using various Maxwell equations. So let's derive this equation. So there are mainly three types of differential equation for entropy calculation, and that can be given by ds is equal to Cp upon T dt minus del V upon del T at constant pressure dP. Second equation that can be given by ds is equal to Cv by T into dt plus del P upon del T at constant volume into dV. And third equation that can be given by ds is equal to Cv by T dt minus del V by del T at constant pressure upon dV by dP at constant temperature into dV. So these all three are differential equation for entropy calculation. So we have to prove these all three equations. So let's prove this equation using concept of heat capacity. We know that heat capacity that can be given by dq is equal to C dt. But at constant pressure, this equation becomes del q upon del T at constant pressure is equal to Cp. So it becomes our equation number 1. Now again this equation for constant volume, which becomes del q upon del T at constant volume is equal to Cv. So it becomes our equation number 2. But we know that from definition of entropy, dq is equal to T ds. So replacing this both dq with T ds, we will get del S upon del T at constant pressure is equal to Cp upon T. For this equation number 1, this becomes our equation number 3. Similarly, for equation number 2, replacing this dq with Tds, then this equation becomes del S upon del T at constant volume is equal to Cv upon T. So it becomes our equation number 4 from equation number 2. Now let's take concept of exact differential equation. So what is meaning of exact differential equation? Let's understand it. We know that entropy is function of temperature and pressure. So can write that S is equal to function of pressure and temperature. Now if we want to differentiate, or can say that if we want to do exact differential equation for this system or this term, then what we have to do? First we have to write exact differential equation ds is equal to differentiation of entropy using first term. So let's write del S upon del P. We have to do partial differentiation of entropy using first term by keeping second term as a constant. So let's take this temperature as a constant. Multiply with total differential equation of given term. So total differential equation of pressure plus, now same thing we have to do with the second term. So del S upon keeping pressure constant and partially differentiation with temperature, so it becomes del S upon del T at constant pressure into dt, which is our total differential equation. So this equation becomes our equation number 5. But we know that Maxwell equation that can be given by del S upon del P at constant temperature is equal to minus del V upon del T at constant pressure. So using this Maxwell equation in this equation number 5, we will get ds is equal to replacing this del S upon dP at P with minus del V upon del T at constant pressure plus del S upon del T at constant pressure dt. Now we have to replacing this term with using equation number 3. So using this equation number 3, there is a term del S upon del T at constant pressure is equal to Cp dt. So we have to replace this del S upon del T at constant pressure with Cp upon T. So easily can replace this del S upon del P at constant P upon with Cp upon T. So by replacing this term, we will get ds is equal to this term as it is minus del V upon del T at constant pressure into the dP, because there is a dP here, this dP here, then plus del S upon del T at constant pressure, that replaced by the Cp by T. So we have to write Cp by T here into dt. So this equation becomes like this: ds is equal to Cp by T into dt minus del V upon del T at constant pressure into dP. So it becomes our first equation which we have to derive, or can say that equation number 6. So this is our first equation which we have to derive in this equation 1. So we derive this equation. Now we have to derive this equation number 2. To derive this equation number 2, let again consider S is equal to function of volume and temperature. So this equation becomes like this: ds is equal to del S upon del V at constant temperature into dV plus del S upon del T at constant volume into dt. So first we have to do partial derivation with first term. So doing first partial derivation of this entropy, then again derivation with total differentiation, so dV, plus then have to differentiate with second term which is temperature. So partial derivation with temperature. While going to differentiate with partial derivation, we have to construct some term. So if we are going to differentiate with, there is a constant temperature, and if we are going to differentiate with the temperature, then it becomes volume constant, and then exact differential equation, or can say that total differential equation, which is a dt. Now again we can replace this del S upon del T at constant volume using this equation number 4. So using this del S upon del T at constant volume is equal to Cv upon T. So let's replacing with Cv upon T. So this equation becomes del S is equal to del S upon del V at constant temperature into dV plus Cv upon T into the dt. And we know that Maxwell equation that can be given by del S upon del V at constant temperature is equal to del P upon del T at constant volume. So replacing this del S upon del V with this equation, we will get ds is equal to del P upon del T at constant volume into dV plus Cv upon T dV. So rearranging this equation, it becomes Cv upon T into dV plus del P upon del T at constant volume into dP. So it becomes our equation number 2 which we have to derive, and this becomes our equation number 7. So this is the same as the equation number 2 which we have to derive. Del S is equal to Cv upon T dV plus del P upon dt at constant volume into dV. So it's same as our equation number 2 which we have to derive. So this becomes our second equation number 2. Now we have to derive this equation number 3. So let's derive it. To derive this equation number 3, we have to take exact differentiation. V is equal to function of temperature and pressure. So this equation can easily do exact differentiation, taking differentiation, or can say that taking partial derivation with t, then it becomes del v upon del t. By partial derivation with t, keeping pressure as a constant, or can say that keeping second term as a constant, multiply by total differentiation, so which is dt plus del v upon del p, by keeping first one is a constant, so it's constant temperature, into total differentiation of which is a dp. By taking constant volume, above equation becomes, this term becomes 0 for constant volume, then del v upon del t at constant pressure is equal to del v upon del t at constant temperature, and del p upon del t at constant volume. Taking volume is a constant, so it becomes, taking this to this side, and del t upon del p, so it becomes del t upon del p at constant volume, and this is going to this side, so it becomes minus sign, so taking this minus sign here. So this becomes our next equation. Now again rearranging equation, we will get del p upon del t at constant volume is equal to del v upon del t at constant pressure upon del v upon del t at constant temperature. Now value of this equation put in previous equation number 7, we will get ds is equal to cv upon t dt minus del v upon del t at constant pressure upon del v upon del t at constant temperature into dv. So it becomes our equation number 3, which we have to derive. So this becomes our answer for the equation. So can say that hence prove this all three equations which relate, or can say that which is used for the calculation of entropy. So these all are various form of differential equation. First equation that derived like this is the first equation, then second equation which is here, and third equation that is derived from this. So this becomes our final answer. So these all are various differential form of entropy calculation. So this is all about today's lecture. I am completing my lecture here. Thank you.